All right, guys. So today I just wanted to post a short video on LU factorization, right? Um, I think in the last class we sort of touched a little bit on that, but I just wanted to cover that in pretty much in detail, right? Because this will be super important for your midterm exam. Um, so so basically I covered a lot on gauge elimination, but um the next step is the LU factorization, which basically comes from Gauss elimination. And I also talked about that LU factorization is much more faster than Gauss elimination because it's the order of complexity is of n square compared to n cube, which is basically it scales quadratically, right? So compared to cubic for Gauss elimination. So definitely it's going to be having a huge advantage over when you take basically when you do like inverse computations for solving linear systems. So that's something which you're gonna see basically when you increase the number n for your matrix, right? So then you will see if you keep like 10,000 versus let's say 100,000. So then you're gonna see that Euler factorization performs much better than Gauss elimination. So that's the general idea so far. Um, but right now I'm just gonna go through two example problems. So this will be helpful for a better understanding. All right, I'm gonna share my screen right now. Okay. Um, all right, so here is one example that says so the topic of today's sort of end goal of the discussion is LU factorization with pivoting consideration. This is the first example where um, we'll be checking the with pivoting, right? Um, Let me see. Actually, it is the first one is without pivoting. There is a typo here. I'm gonna fix that. The first example is without pivoting because there is no need of pivoting. If you see, even if you do that, it's gonna see that the answer will be the same, right? Because here the numbers are arranged in such a way that the maximums are always on the diagonal. So the diagonal terms are always gonna be the maximum for each column. So you don't have to do any row swap. So basically, your P matrix is going to be identity. So that's how we define the with or without pivoting. So first one is without pivoting. There's a typo here. The second one will be with pivoting. So that's a little bit more tedious in terms of your keeping track of all of the multipliers where you're gonna be assigning them to each of the respective locations for this P matrix. So we'll see more in a while, but let's get started with the first problem. So the first problem says 2x1 minus x2 equals to 1, minus x1 plus 2x2 minus x3 equals to 1, and then minus x2 plus 2x3 equals to 1. So let's just write it in a matrix vector format where vector unknowns are x1, x2, x3. The right hand side is just 1, 1, 1. The A matrix is represented by this, right? Um, and then, so as I mentioned, we examine where, row changes are necessary for comparing the pivoting elements in each column, right? So the maximum, if you see here, it's already gonna be, 2, which is on the diagonal. So that's why we don't have to basically go ahead for the partial pivoting steps, right? So this is what is said. Each pivot is largest in magnitude with each within its column below the diagonal. So that's why it is the partial pivoting is not a required step here. So then let's proceed with the LU factorization, right? So for LU factorization, here, so P is gonna be identity, right? So basically P equals to LU, right? P is gonna be identity, so A equals to LU, right? So The motivation here is that L has to be written in this format, right? Where you're gonna see L21, L31, L32. These are the three elements for the L matrix, right? And then for the U matrix, you're gonna see you have in a similar way for the upper diagonal terms, basically. So it's gonna be U11, 12, 13, 22, 23, and then 33. The rest of the terms are gonna be zero because it's upper diagonal, and L is basically lower diagonal. So lower diagonal, that's why L, upper diagonal, that's why U. So that's how I, sort of intuitively remember without keeping in mind whether L is upper or lower. So that's how we do it. All right, and then so let's see the first step. So first step, first row of U is equal to first row of A, right? So first of all, you have to assume that U equals to A, right? And then U11 is nothing but 2, 12 is minus 1, 13 is 0, right? Because this is the first row, okay? And then what we have here is the step which we do in Gauss elimination. So L21 is nothing but your the A21 upon A11, right? So minus 1 over 2, okay? So this is gonna be minus 0.5. And then if you do the transformation, which basically rho 2 equals to rho 2 minus half times rho 1, right? So that's gonna give you this updated rho 2 basically. Now L31 is gonna be 0 because A31 is already 0, so rho 3 remains unchanged, right? And then the next step is to compute L32 basically. So for 32, what we have here is basically minus 2 over 3. And the reason is that you have 3 over 2 here and minus 1 here. So A32 upon the transformed row, which is 0, 1.5, and minus 1. So basically, minus 1 upon 1.5 is going to give you minus 2 over 3, right? So L32, we also got that. And then transform the row, right? So this is your transform row. If you do that, you're going to see you will get 0, 0, and 2, basically. So that's your final step, basically. So right now, you don't have to keep track of P because P is already identity. So your L matrix here is nothing but if you know these three values of L, right? L21, L31, L32, you are good to go to plug in those values at this location and then you will get your L matrix, okay? And for you, um, let me see. Yeah, so for you is nothing but your transformed A basically, because you initially assume U to be A, but then when you keep on transforming A, you're gonna see the lower diagonal terms will keep on um, going to 0, right? So these all three terms have now become 0, right? And then the diagonal terms have also changed here, right? So if you see here, um, we got like 1.5 here, right? This is your second row, by the way. And then this is your third row, which is the transformed third row, basically. So this is what is 0, 0, and 2. And 2 minus 1 is 0 is coming from this. So this is not touched at all. So this is as it is from the beginning. So now the next step is, even though you have done all the steps correctly, but still it's important to check if your steps are correct, right? As a sanity check, you know that it is correct, but how do you know that it makes sense? So do the check, which is P equals to LU, where P is nothing but identity here, because there is no partial pivoting. So if you do that, you're gonna see LU equals to A. If you do that, um, do the left hand side, right hand side comparison, you will see the condition is satisfied. So which means your answer is correct. Now, now comes your next step, which is our main intention to do this all the way order of n square operations. So to get the unknown vector x, right? So what we do here is that we transform A to B LU, right? So basically LUX equals to B, right? Here P is I, so you don't have to worry about that. So now, so we then say that um, LUX equals to B, right? You say UX equals to Y, and then you say LY equals to B, right? So LY equals to B, you first solve that, right? Using your forward substitution. So if you see, right, these three equations, you're gonna see first you will get Y1. Now from first equation, substitute that into 2, you're gonna get y2. From first and second, you're gonna get y1 and y2. Substitute that into 3, you're gonna get y3 basically. So this is how you approach in a forward manner where you keep on getting y1, then y1 and y2, then y1, y2, y3, then y1, y2, y3, y4, right? In that manner, you keep on marching forward and obtain all the values from top to down. So this is a top-down approach, right? That's why it's called forward substitution. And then once you get the y vector, remember y is not our actual solution, right? Our actual solution is x. So next step is to just check, not check, is to just solve these three equations where you have ux equals to y, right? So you already know you already know y. All you need to do is just do back substitution, right? So if you write down these three equations, you're gonna see you have to follow a bottom up approach, right? So in the last step, you're gonna get x1, and then in the second step, substitute x1, you're gonna get x2, and then in the first step, you're gonna see you'll get your x3. Okay. Um, Yeah, sorry. So this is actually written in a reverse way, but the way it is actually back substitution, where in the last step you get x3, and then you get, if you solve this equation, you get x2, right? And then if you solve the first one, where you need x3 and x2 to get x1, so from there you get x1 basically. So it's like obtaining x3 first, then x2, then x1, and so on. So it's like a bottom-up approach, right? Um, so I think this makes sense so far, but so this is what I say PA equals to LU, right? In case there are no row exchanges we require during factorization, the permutation matrix is simply the identity matrix. So so that's why we say that L equals to PA or A because P is identity. So this completes this example. I hope it's clear to everyone. Um, I know that there are no audience today right now because it's just me talking to myself. But I hope it'll be helpful when you check the recording. So I hope, yeah, so it's still recording. I hope it is clear. And then we'll see one example with pivoting, right? Where your P is not identity anymore, right? And this is what is something you should be practicing as well, because you cannot expect P to be identity every time, right? If you are lucky, then it is identity. Otherwise, it is not. So let's see an example where it is not, and then we need to do the with pivoting step, right? Which I already discussed in the last discussion, right? In the office hours. I think it was not an office hour, it was the previous to that discussion. So yeah, discussion 1A basically. So I recorded that session. You can take a look. Um, so let's get started with the with pivoting step and then combining value factorization. So in this problem we have as usual three equations, three unknowns. These are all linear equations. Now the A matrix can be represented as in this format, right? 1 1 1 2 3 1 2 1 2, and then B is nothing but 6 14 and then 10. So now you need to check the maximum thing, right? Which is the column and pivot candidates. So if you see that, you're gonna see, so 2 and 3 are the equal, right? These are 2, 2, both are equal. So here's the interesting question. Which row should you choose in this situation? The simple answer is you are free to choose any of the second or third row, because if you see maximum of this column is nothing but 2, right? So you're free to choose either second or um the third column basically. So now that you have seen which value makes sense to you for a pivot candidate, so let's say if you have um, chosen the second one, right? So then you need to swap the first with the second row. Now, once you do that step, right, you need to remember initially P was your identity matrix, right? It was 1 0 0 0 1 0 and then 0 0 1. Swap the first and second rows. You're gonna see 0 1 0 will come top and then 1 0 0 will come in the bottom. So that's how you swap the first and second rows basically. And then you need to multiply this P with the A, right? So that's how you get the PA matrix again, basically. So this is gonna give you um the first row and second row is gonna swap, right? That's what is the intention of P, right? Swapping rows. So if you do that, you see 2 3 1 1 1 1 and 2 1 2. So first and second row are basically swapped right now. Now, um, yeah, I don't know what this is, probably a typo or something. So PA equals to LU, right? This is what your next um sort of step is, okay? And then let me see. So yeah, so basically we'll be doing the same steps again, right? You don't have to actually make any more row changes because you're already satisfied with this format, right? So 2 1 2. Um, yeah, so what I was gonna say that uh once that we are satisfied with this operation, um, right? So the thing is that if you see, so the way we check the maximum condition is that for each I, right? Let's say I equals to 1. So then you see if all the elements below that are a little smaller than this, right? So for I equals to 1, 1 and 2 are smaller than 2. Okay, that makes sense. For I equals to 2, 1 is smaller than 1. That is also makes sense. Now smaller, it's like not in the sense strict inequality. It's like if it is equal, it's gonna be fine. And then 2 is nothing but 2, so there is no element below 2. So basically this whole numbers make sense so far because all of the elements below the diagonal are smaller than the diagonal elements. So that's how we stop doing the row switching operations. So anyway, next important step here is to again evaluate the u thing which we did right here. If you remember u11, u12, u13, and all of that. Okay, so once you check that, you're gonna see you have u11, u12, and u13 to be 231, right? Remember, this is the switched rows operation we did a little before. Um, and then so for right now you have L21 to be 1 over 2, right? So basically this element over this element, okay? So this gives you 1 over 2. L31 gives you 2 over 2. Okay, I hope this is clear. And then transform the row to basically to be row 2 equals to row 2 minus L21 times row 1, right? So that's gonna give you 0 minus 0.5 and then 0.5. Now this is what your row 2 transform looks like, okay? And then for row 3, row 3 is nothing but 1 over 1. So L31 is gonna be 1. So row 3 equals to row 3 minus 1 times row uh, yeah, row 3 equals to row 3 minus L31 times row 2, right? So no, actually row 3 equals to row 3 minus L31 times row 1, right? We are still using this as the pivoting. Um, so basically you are doing two operations, row 2 equals to row 2 minus L21 times row 1, and then row 3 equals to row 3 minus L31 times row 1. So if you do those two operations, first one will give you this, second one will give you this, right? So this two you should keep in mind so far. Um, And then, so your U22 becomes minus zero point 0.5, right? Here, your U23 becomes zero point 0.5, okay? And then L32 is gonna be this value upon this value, okay? So minus 2 upon minus zero point 0.5, right, is gonna give you 4, okay? Now you have one more operations left, right? So it is nothing but row 3 equals to row 3 minus L32 upon row 2, multiplied by row 2, right? So row 2 is this row basically, which is the one we got a little back before. So if you do these operations, row 3 equals to row 3, right? This is your row 3, this is your row 2. So row 3 equals to row 3 minus L32 times row 2, okay? So if you do that, you're gonna see it'll give you 0, 0, and minus 1, okay? Um, so your U33 is nothing but minus 1. So if you arrange this in the order, you're gonna see that this is your second row, right? This is your second row. The untransformed row was the third row was this, but then when you transformed it, it became this, right? So then you put it like 0, 0, minus 1, and initially 2, 3, 1 was the first row, so it is left untouched. So it remains untouched throughout the operations basically. So so next we are done. I mean, all we need to do is just plug in L21, L31, L32 and the right locations. Diagonal is 1, remember, in L matrix. Upper diagonal is 0, and then for lower diagonal is going to be 0. um and then for the upper diagonal is going to be the transform rows basically, where row 1 is 231, which is untouched. Row 2 is 0 minus half half, and then row 3 is 0, 0 minus 1. So I hope this makes sense so far. And then if you want to check whether your answer is correct or not, please do this operation. I'm suggesting you that don't forget this step. It's super important. If you see your PA is not equals to LU, that means there is something mistake in your calculation. So please do that again. Don't try to proceed further if you have not done this step. So please do this step and then proceed for obtaining the unknown values. Okay. Um, so do this step. PA equals to LU. P is already known. A is also known. Uh, so PA is this, right? And then you have known L and U. So multiply LU, you're gonna see it gives you this matrix. Um, yeah, so that means our calculations are correct. And then the next step is just to use the equation AX equals to B, right? So multiply by P in both left hand and right hand sides. You will see PAX equals to PB, right? We write PA to be LU, so we have to solve LUX equals to PB, where we say that UX is nothing but one more vector of unknowns, which is Y. So LY equals to PV, right? So solve this. LY equals to PV, you know L, you know P, you know B. So the right hand side will be transformed to this, right? And then the left hand side is nothing but your L. So if you do that, you're gonna see you will get your Y vector to be 14 minus 1 and 0. Now this is your Y vector. Remember, this is not the actual X vector. So for X vector, we express Y to be UX, right? So UX equals to Y. So then what we need to do is back substitution basically, where first we get X3 and then we get X2 and then we get X1. So you have to follow bottom up approach, right? If you do that, you're gonna see it'll give you simply as an yeah, so it's totally in n squared operations, but these operations are in order of n, right? For x3, you don't have to do anything. To get x2, you should know x3, and to get x1, you should know x2 and x3. So this is like an order of n operations. Um, but remember, as a whole, in total, um, wait, no. So yeah, this I'm sorry, this if you see you if you have like n unknown trade, in a way it is like an n squared operations, not n operations. So my bad. So this is in total n squared operations, right? Which is much faster than nq operations for Gauss elimination, and that's why it's a super strong algorithm in many applications you use when you do the inverse of let's say ax equals to b sort of thing. So if you want to get x, you do a inverse, where you do this steps to get your unknown x basically. Um, so then yeah, so we got this solution to be 420, right? Which is your final answer. You can put it in the equation and see if it makes sense, but I think it makes sense because I see 4, 2, and 0 are satisfying, so it looks pretty much correct. Um, and then yeah, that's it. So basically, the second one is where you need to keep track of this p matrix, right, for the row switches. But for the first problem, you don't have to worry about that. So that's what is uh, segregates the two different worlds of with pivoting and without pivoting. So I hope this is clear so far, and I'm gonna be uploading this recording right now in Brilliant. I'll post an announcement as well that I have created this recording because I was supposed to do this in the last class, but we actually went on answering many questions from the students, and then having the Q&A session was pretty long, so we couldn't do that. But anyway, I'm gonna be uploading this and hope this will be helpful for you. And yeah, I hope this is clear to everyone. If anyone has any questions, please reach out to me by email, or we can have a special office hours as well before midterm, because I think midterm is going to be on 26th, right? So there'll be an announcement as well. But so it'll be on 26th as per we decided with the professor. So, and yeah, I'll post a practice midterm as well by tomorrow. And I hope it'll be super helpful for everyone. So you can take a look at that as well. And then yeah, I think so that's it for now. And we'll see you next week. Yep. So thank you everyone. So